In this problem, we have heat transfer from a hot surface assisted by a set of fins attached to the surface. So we have an array of fins, all made of aluminum, all with the same dimensions, 3 centimeters long, and the spacing information on the plate is given here. The plate itself at 100 degrees C, we're conducting and convecting heat to surrounding fluid at 30 degrees C, convection coefficient, thermal conductivity given, and we want to know the total rate of heat transfer from a 1 by 1 square meter section of the plate. So 1 square meter section of this plate, and also the effectiveness of the fins. Now we'll outline a procedure for finding these quantities. The details are given in section 3.6.5 of the textbook, but we'll summarize it here. So first, we want to calculate the efficiency of a single fin. And we can do that because we know we have pin fins, and we can look up the relevant equation in the table. Then calculate the total surface area of all the fins taken together. So that's going to be the area of a single fin times the total number of fins in the 1 by 1 square meter area. Third, determine the total surface area of the part of the hot surface not covered by fins, what we call the unfinned base area. And that is going to be equal to the total area of the plate, which is 1 square meter, minus the product of the number of fins and their cross-section, the little cross-section that the fin takes up when it is attached to the plate. And then number 4, from the definition of fin efficiency, calculate the heat transfer of the array of fins. So this is our heat transfer from just the fins. It does not include the flat part of the surface here. That is given by the efficiency of the fin times the number of fins and the maximum possible heat transfer that would occur if the temperature were the base temperature across the length of the fin. And finally, we calculate the total heat transfer from the object, and that brings in the heat transferred from the flat part of the plate, or the unfinned region of the plate. So the total heat transfer is the heat transfer through the array of pins plus the heat transferred from the base. So we start with step 1, determine the efficiency of a single pin. We use table 3.5 for pin fins. That gives us the equation to use for calculating the efficiency. Also the equations for determining other key parameters, the characteristic length, the surface area of the fin, and the quantity m. We start by calculating the characteristic length, which is the pin length plus 1/4 times the diameter, or 3.0625 centimeters, and we use that to determine the surface area of the pin. And finally, the quantity m, which we can simplify this somewhat by substituting P for the perimeter of a cylinder, which is pi d, and for the cross-section of the cylinder, pi d squared over 4. So that gives us square root of 4h over kd. We substitute our values in. We get 15.37 for m, and now we can write those quantities up in case we need them later and go about our calculation. Plug in our values, we get 0.932 for the fin efficiency. And make a note of that and go on to step 2, calculate the total surface area of all the fins. And so the total finned area here is the fin area, surface area, times the number of fins. So what is in? How many pins do we have in this area? Well, we're given the spacing. This is the center to center spacing between the fins is 0.6 centimeters, and the pins are arrayed in a 1 square meter array. Then the total number of pins is going to be 1 square meter divided by the square of the spacing, 0.006 meters squared. And this gives us 27,777 pins, we just round to a whole number of pins here, and it's a lot of pins. This calculating it this way does allow for some little bit of spacing between the fin and the edge all the way around. And then we multiply n by the surface area of a single fin to get the total finned surface area of 6.68 square meters. We move to step 3, determine the total surface area of the surface not covered by pins. This is the unfinned base area. We calculate now, and here's our equation for it: the total area minus the all of the cross sections taken up by pins on the surface. That's going to be the number of pins times the cross-sectional area of each pin, or 1 minus 27,777 times the cross-sectional area, or 0.86 square meters. And so we note the base area, the unfinned base area, 0.86 square meters. And we move on to step 4, to calculate the heat transfer from the entire array of fins. So that's going to be equal to the NAF, that's the total surface area of the finned surface area, times the fin efficiency, times H times the T of the base minus T infinity. And we plug in our numbers, and we get 15,253 watts. That's the rate of heat transfer from the fins alone. And then finally, the total heat transfer from the object is the sum of the heat transferred from the fins plus the heat transferred from the unfinned base of the plate. And we've calculated the heat transfer from the array. That's 15,253 or 15,254. And then we add to it the heat transferred from the unfinned part of the surface, which is the area, the base area, A subscript B. We plug in our numbers, and we get 2107 for the heat transfer from the base, unfinned base area. It's a lot smaller than the heat transfer from the fins. And the sum is 17.4 kilowatts. And now to determine the effectiveness of the fins, this is the total heat transfer from the finned object, which we just calculated, and divided by the heat transfer from the flat surface if it did not have fins covering it. So that would just be the total area of that surface times H times the temperature difference, theta B. And so we substitute in our values, and we get an effectiveness of 7.10.